Good morning to all. Discuss the determination of molecular weight of a polymer, that is polyvinyl alcohol, by viscosity method. Okay. We are going to find the molecular weight of a polyvinyl alcohol by viscometer method. Okay, this viscometer will be working based on the gravitation only. Okay, by gravitation principle, we are. So before going to discuss about this experiment, first we should know what is polyvinyl alcohol. Okay, vinyl alcohol means a double bond which is attached to OH is vinyl alcohol. That is the monomeric unit. If you polymerize the vinyl alcohol, you get polyvinyl alcohol. So now, before going to do the experiment, it is our duty to discuss about viscosity. Okay, what is viscosity? Viscosity is nothing but, see that we can consider it as an internal friction of a moving liquid. That is the one definition, or otherwise in other way, force per unit area to resist the flow. Okay, that is known as viscosity. Even or otherwise, we can define viscosity is a measure of resistance to flow. Okay, with simple words, we have defined the viscosity. I think with these definitions, you can understand what is the viscosity. It is an internal friction of a moving fluid, or otherwise force per unit area resisting a flow, or otherwise a measure of a resistance to flow. Okay. We are having two types of viscosities: dynamic viscosity and kinematic viscosity. Okay, you see the differences between the dynamic and kinematic viscosities. Is dynamic viscosity is nothing but ratio between shear stress to shear strain. Okay, this kinematic viscosity is the ratio between dynamic viscosity and the density is known as kinematic viscosity. So we can determine the viscosity in two ways. One is by using rheometer and viscometer. At present, we are going to go find the molecular weight by using viscometer method. The aim of the experiment is determination of polyvinyl alcohol molecular weight, and glassware and chemicals we are using in this experiment, and principle of the experiment, and experimental procedure, and calculation and result. Okay, this is the overview of our experiment. Glassware and chemicals required for this experiment are viscometer and stopwatch, and SMFs, pipette, and preparation of 5% PVA, and preparation of 0.25, 0.5, 0.75, 1.25 percentages of polyvinyl alcohol, and fifth one is rubber band. Okay, so we need all these tools or the glassware and chemicals required for this experiment. Yes. First, what we do, we will prepare 5% of polyvinyl alcohol. We prepare 5% of polyvinyl alcohol. How will you make the 5% of polyvinyl alcohol? Let us dissolve the 5 grams of polyvinyl alcohol in the water. Okay. Is, you will be getting 5% of polyvinyl alcohol. From that polyvinyl alcohol, what we do, we will prepare 0.25, 0.5, 0.75, 1 and 1.2. So based on our V1, N1 is equal to V2, N2, we can prepare these solutions. That is 5 weight percentages of polyvinyl alcohol solutions. For that, what we require 5 SMFs, 25 ml SMFs, that is standard measuring flasks. This is the viscometer, YouTube viscometer we are using. Okay, this is the calibrated volume from this point to this point in this video now. So here we are having a capillary tube, okay, left side. So the principle behind in this experiment is Markov equation, or our experiment will be based on this equation. What is the equation? Markov equation. What is the Markov equation? Neta I equal to Km power alpha. Here neta I is intrinsic viscosity and K and alpha are Markov constants. Okay, K is equal to 5.43 into 10 power minus 4 deciliter per gram at 30 degrees centigrade. Okay, it depends on temperature. This K is depends on temperature, both the things, alpha and K. Alpha is 0.64. Alpha value for the polyvinyl alcohol is 0.64. K value for polyvinyl alcohol is 5.43 into 10 power minus 4 deciliter per gram. Factors affecting the viscosity. One is temperature. If you vary the temperature throughout the experiment, the result may not be a reliable result. We have to maintain the constant temperature, and we are going to test the effect of concentration and viscosity, or the viscosity value, and we are going to maintain constant molecular weight of a polymer throughout the experiment, but we vary the concentration. And solvent used in the present system is water. The solvent used in the present system is water. Okay, these are the 4 factors which are affecting the viscosity of a polyvinyl alcohol. Yes, this is one of the important slide to discuss. The thing is, this is the graph which is explaining the relation between reduced viscosity and concentration. We are taking 5 concentrations of polyvinyl alcohol, that is 0.25% and 0.5% and 0.75% and 1% and 1.25%. Okay, 5 concentrations we are. What is reduced viscosity in this case? Just we are having 3 viscosities, reduced and intrinsic, and one more, the relative. Okay, let us see what are those maybe in next slide. Prior to that, let us discuss the preparation of various weight percentages of polyvinyl alcohol, how we are making. For these experiments, we require 6 25 ml standard measuring flasks. Okay, within that, what we are doing first, we are taking in first SMF, we are taking 0 ml of polyvinyl alcohol and 25 ml of water. In second SMF, 1.25 ml of 5% polyvinyl alcohol and 23.75 ml of water. In third SMF, 2.5 ml of 5% PVA solution and 22.50 ml of water. And in fourth SMF, 3.75 ml of 5% PVA solution and water is 21.25. And in fifth SMF, 5 ml of 5% PVA solution and 20 ml of water. And in sixth SMF, 6.25 ml of 5% PVA solution and 18.75 ml of water. Okay. With these proportions, we will get 0.25%, 0.5, 0.75, 1, 1.25% of PVA respectively. Okay. For the preparation of various weight percentages of PVA, we have to mix 5% of PVA solution and water in these proportions. Okay. Once if you mix, what you have to take? We have to take first SMF, that is, which is having water only. Okay, from that SMF, we have to pipette 10 ml of water by using 10 ml pipette. We are pipetting now. We have pipette. Exactly, we have to take the 10 ml of water. So once, if you take the water in pipette, we have to release the water into the viscometer. So on right side tube, okay. Once if you release the water from the pipette in right side, what? So you have to release entire water into the viscometer. Even single drop of water should not be there in the pipette. Okay, finally we have to blow that water also into the viscometer. So once if you take the water into the viscometer by using our rubber bulb, we have to suck the water on left side. You see that calibrated value, and we have to control the flow of water. See, we have to control the flow of water by closing its lid on left side. Slowly we have to release the water. Just you see here. Slowly we are releasing. Just clearly we are seeing it. You see that? Yes. Exactly at that point we have to stop it. And we have to switch on our stopwatch. Okay, both at a time. Simultaneously, parallelly, we should release the finger as well as we should switch on our stopwatch at a time. This is a very, very important moment during our experiment. You see that at a time, finger and the stopwatch should be, yes, both should be released at a time. Okay, once if you are releasing the yes, once again we are doing in this video. Yes, yes, at a time we have. So now what will happen? Right side, the pot or in viscometer, we are having a capillary tube. Through the capillary tube, our water will travel. Now, you see that as per our viscosity definition, we are measuring the flow time. So we are measuring the flow time for water now. Okay, so we have measured the flow time of a water and we have note down the value in our observation book. And we are taking second SMF, that is 0.25% of polyvinyl alcohol. Again, the same procedure. We are pipetting 10 ml of 0.25% of polyvinyl alcohol into the pipette, and we are taking that 0.25% of PVA solution into our viscometer. Okay. Exactly, we should take 10 ml only. Yes, once if you take the 10 ml, we should, prior to this, we can rinse it with water once. You can release our 0.25% of polyvinyl alcohol into the viscometer. Okay. Yes, it is better if you are keeping your viscometer in 45 degrees. We can avoid the formation of bubbles in the viscometer. At the end, we have to release the entire solution. Okay, this is the second measurement we are doing. Just we are taking our rubber bulb and we are applying the pressure, and we have to close on the left side lid, and we have to keep our rubber bulb on right side, and we have to suck the 0.25% of PVA solution. Okay. Once if the solution has reached on the right side lid, okay, we have measured again the flow time for the second bottle, SMF bottle, and for third SMF, again, we have to pipette the 20 ml of 0.5% of polyvinyl alcohol solution, and we have to transfer the solution into our viscometer. Okay, each time it is not necessary to wash our viscometer. The reason is we are doing our experiments from lower concentration to higher concentration. The effect of the washing may not be an influencing factor at this case, because we are doing our experiment from low concentration to higher concentration. It is not necessary to wash. Okay. So now we are taking a third SMF solution, that is 0.5% of polyvinyl alcohol into the viscometer. Yes. And again, we are taking our rubber bulb, and we have to close one side lid with our finger, and one side we have to suck the PVA solution. Okay, you see that in that case only it will be yes. Once if you are ready with the stopwatch and solution, PVA solution, yes, we have to start both at a time, and we have started already. Now we are going to measure the flow time for the third percent, that is 5% of polyvinyl alcohol. In similar manner, we will be doing for three more concentrations of polyvinyl alcohol. Okay. Now we have to stop exactly. Yes, we stopped, and you note down the flow time in your observation book. Okay, we have noted it. Okay, and we are going for fourth measurement. Now 3 measurements over. Okay, water 0.25 and 0.5% over. Now 0.75% of polyvinyl alcohol we have to take 10 ml from the 10 ml pipette, and we have to transfer the 0.75% of PVA into the viscometer. It is better to keep 45 degrees. We can avoid the formation of bubbles inside the viscometer. During the measurement, there should not be any bubbles inside the viscometer. That is important thing. Again, you have to take a rubber bulb and on right side you have to suck the PVA solution. Yes. And is both at a time you should switch on. You have to switch on the stopwatch as well as you have to see the flow. The time required for PVA to flow from this position, from this mark to this mark. Okay, two marks are there. Now the liquid is flowing. At the bottom, capillary tube is there. That means through capillary, it is flowing. Now exactly whenever the solution is reaching that mark, we have to stop our stopwatch. Okay. Once if you stop it and you have to note down the time in seconds, sometimes what will happen, it will cross even 60 seconds. That means you can write it in 1 point. Again, now one more concentration, that is 1% solution we are doing. See that? We have done 4 concentrations up to now, 5 concentrations. That is, first one is 0% or 0 concentration. There is no PVA in first. That is a solvent only, that is water. We are using water as a solvent in this PVA water system. Okay, PVA is a solute and water is a solvent. See, again, we are measuring the flow time for this concentration. For 1% of PVA solution, yes. See now the liquid EVA solution is flowing. We have to find out the flow time from the two marks, okay, whatever we are having in viscometer, okay. Now last concentration, that is 1.25% of polyvinyl solution, okay, 1.25% of polyvinyl alcohol with the help of pipette. We are taking 10 ml of 1.25% polyvinyl alcohol. Procedure is same for all the measurements, only we are varying the concentration of PVA. Same thing, just we are taking rubber bulb and we are sucking the polyvinyl alcohol to the right side, and exactly once the PVA is reaching the mark, we have to close it. Okay, now we closed, yes, we closed it, and go to the stopwatch at a time, and you release the stopwatch as well as your finger. Okay, if you release both at a time, now you can see if our PVA solution is reaching second mark, exactly that time you should switch off your stopwatch, and we have to count the flow time, or we have to see the number of seconds in stopwatch. Okay, you have to see the number of seconds in stopwatch. Yes, for all the 6 experiments, yes, the time flow for water and time flow for the 0.25, 0.575, 1.0, and 1.25 were written in the table, okay, in observation table. For water, it took 16 seconds, for 0.25%, 21 seconds, for 0.5, 34, for 0.75, 45, 1%, 70 seconds, for 1.25%, 111 seconds, okay. So now, as I told you, 3 types of viscosities. You see that the ratio between the reference and the flow time of our polymer and water or solvent will give us the relative viscosity, and the specific viscosity, if you subtract 1 from the relative viscosity, you will be getting specific viscosity, okay. And reduced viscosity means the specific viscosity divided by the concentration of our polymer will give us the reduced viscosity. These are the 3 viscosities we are observing and we are calculating according to the thing, according to the formula, okay. One is water flow time is 16. Now T0 is 16, T is this 21, 34, 45, 70 and 111. Okay. Now we are dividing our T values with T0 value, that is commonly by 16. 21 by 16, 34 by 16, 45 by 16, 70 by 16 and 111 by 16 will give us 1.3125 and 2.1250, 2.8125, 4.3750 and 6.9375. This is these are the values related to relative viscosity. Okay. Now, if you subtract 1 from this relative viscosity, you will get specific viscosity. That is NS neta SP. The values are 0.3125, 1.1250, 1.8125, 3.3750, and 5.9375. Now, if you are dividing this specific viscosity with the concentration of the PVA, you will get the reduced viscosity values. Now, if you divide this column values with 0.25, 0.5, 0.75, 1.0, and 1.25 respectively, we get 1.25, 2.25, 2.1466, and 3.3750 and 4.7500. Okay, these are the reduced viscosities. Now, what we do, we are going to draw a plot between NSP versus the concentration of the polymer. If you draw the graph between these two units, what we get, if you draw the plot between like how we have seen in our equation, our basic principle equation. Okay, Mark Hawking equation, just we will get a straight line which is intersecting y-axis. The intersecting point we are taking as a neta I, that is intrinsic viscosity. We are plotting a graph between NSP by C versus C values. Now, if you plot a graph, what we get? We get a straight line which is intersecting y-axis. The intersecting point, we are considering it as an intrinsic viscosity, that is neta I. Neta I we are getting from graph, log neta I from graph. And we know the alpha value and K value for the polyvinyl alcohol system. Now, if you know the three things, that is neta I and K value and alpha, we can find out the fourth parameter, that is molecular weight. Once if you apply the log on both sides, log neta I equal to log K plus log M power alpha, log A power N, N log A. Yes, according to that, if you write log neta I equal to log K plus alpha log M, and if you substitute for our present values, if you draw a graph, the intersecting point, that is intrinsic viscosity, we are getting is 0.5. From the graph, we are getting 0.5. Okay. And log K value, that is 5.43 into 10 power minus 5 plus 0.64 log M. Okay. Now, if you apply again log A power N, log M, N, log M plus log N, and if you do the calculation for this, what we get? Log 0.5 is minus 0.3010, and log M plus N, log 54.3 plus log 10 power minus 5. And if you do the calculation for this experiment, and finally you will end up with log M equal to 4.6317. Okay, and if you want M, we have to send log that side. Now, anti-log of 4.6317 will give us the molecular weight of the polyvinyl alcohol. That is 42,825. 42,825 will be the molecular weight of our polyvinyl alcohol. And finally, we are writing the result part, that is 42,825. 42,825. The molecular weight of the given PVA is 42,825. Okay, this is the result of our experiment, and it is my duty to express my acknowledgement to my research scholars, J. Jaikant and Cassandra, asking for their help for the preparation of the solutions and for recording the video. Okay. Thank you for your patience.